Hi everyone, I am Amin. In this video, we will learn how to simulate a CHT simulation of a water jacket and engine block. In this paraview result, you can see the contour of temperature on the engine block and the streamlines inside the coolant jacket. Let's see how we can simply do this on the CONVERGE CFD software. And be sure to subscribe so you don't miss future videos. Here I prepared my engine block STL file. I don't want to simply drag and drop to the CONVERGE. Instead of that, we go to the import STL and make sure that we import it with the correct scale. After you import it, go to the diagnosis and find any problems with your geometry. You can see there is no problem in my geometry. Make sure to save your project after every steps. First of all, we need to name our boundaries. For that, you can go to boundary and find fence between boundaries automatically. This time I want to do it manually. For this, make sure you turn on geometry shortcuts with this G key on the toolbar or from the CONVERGE preferences. Here, simply by pressing the M key, you can mark the edge as boundary fences. Select choosing by arc. Now choose the edges that are related to the water jacket, like inlets and outlets. Here these small holes at the top are the connection between block and head water jacket. Because we only simulating the block, we choose these holes as outlets. We need water jacket domain. Let's make it blue. Liners as the main heat sources. Inflow and outflow boundaries. Let's make outlet red. And also let's change the block's color. And I want to make the inlet green. So for selecting the water jacket walls inside the block, you just simply choose by boundary fence and click inside the fences. This will select all the walls inside these boundary fences. Now here we simply extracted the water jacket domain. Let's name the engine block. For the liners, you can simply make fences or you can use select by angle. Here we need to fill the inlet and outlet of the water jacket to specify them as a boundary. Choose line selection by arc. As I mentioned before, if you enable the shortcuts for geometry by pressing the O key, you can patch using selected edge loop to the center of the loop. Also for non-circular places, you can use P for patching using the selected edge loop. These do the same job, but you can have organized facets with O key. It's better to specify the names of boundary after each patching. Now let's go for outlets. I just simply choosing the arc and pressing the O key. By selecting by boundary and choosing the outflow and clicking apply, we can specify the outlet boundaries. If you see in detail, the lines on these boundaries we patched turned purple. These lines known as non-manifold problems, because here we have three boundaries that are connected together. Also, if you go to the diagnosis panel and find again, you will find non-manifold problems here. This is because we didn't set up our regions yet, and CONVERGE at first know this geometry as a single region. Ignore these errors because they will be fixed later. After the naming boundaries, the second step is fixing the normal orientations. All of them should be towards the flow inside the domain. For non-uniform normal orientations, you can use fixed selections. Now we're done with our geometry. You can use a lot of tools inside the geometry panel to manipulate your geometry to prepare for simulation. Here I want to close unnecessary panels. In the case setup, for the application type, we need to choose time-based. Also, we don't have gas here, and we need to choose liquid and solid simulation. For the physical models, you need to turn on turbulence modeling, also supercycling with the nuclear boiling model. For the grid control, you can enable adaptive mesh refinement with fixed embedding. After that, click down and go to the liquid simulation. Here we need to add our water. For the solid part, you can add your materials like aluminum. Let the global transport parameters be default. And also for the species, you need to add your liquid and solid. In the RAM parameters, change the solver to steady state. Disable the species solvers, and also you can make screen print level to more verbose. Let the steady state monitor be, and we will set up it after we specify the boundaries. For the simulation time parameters, it does not matter how long you take the end time. For the initial time step, you can give 1e-7, also for minimum time step. For maximum time step, you can give 0.1 seconds. Increase the maximum convection CFL limit to 20 and maximum diffusion CFL limit to 15, and also maximum Mach CFL limit to 500. In the solver parameters, select the pressure-based solver type, and here also you can choose piezo or simple simulation schemes. The piezo one is faster, but the simple one is very accurate. For the flux scheme, you need to set 1e-5 for step limiter tolerance, and also enable limit fluxes equally in all directions. Here you can see upwind factor for the momentum finite volume solver. 1 is first order upwind and 0.5 is second order central. I want to solve the momentum with the first order upwind. Here let the parameters be default. At the Equations tab, I need to increase the convergence tolerance of momentum to 1e-6 and increase the max iteration to 100. For the pressure, you can change the solver type to this one to increase the accuracy. Also here I want to increase the energy tolerance to 1e-6 and max iteration to 100. Before going to the regions, you need to specify the streams of fluid and solid. In the stream manager, For the stream ID 0, I want to name it fluid and add a stream flow, which is the solid one. You can add your regions from here. For the fluid, we have the coolant region. And for the solid, we have the engine block region. Now go to the regions section and specify the initial boundary condition inside the regions. Here I want to add the water spaces for our region. But you can see I can't find it because it comes with its formula. And if you don't name it in the liquid or solid simulation panels, it will be very hard to find them inside your species. Here we need to specify which domain each boundary belongs to. Consider the wall boundary condition for the engine body. We must choose the interface for the cooling boundary. We need to select the boundary of the wall for the liners that belongs to the engine body, and also specify the inflow and outflow boundaries. I want to choose the convection type for the wall temperature boundary. In the cooling boundary, as you can see, forward side and reserve side are the same normal orientation directions that we set earlier. Here the forward side shows the direction inside the coolant domain, and the opposite side shows the direction of the engine body. After that, select the coupled option. Here, because one side of the domain is water and one side is solid, we have to consider the wall boundary condition for the fluid direction. Therefore, if we consider the roughness constant to be 0, then the program will think that is a no-slip condition, so it will give an error. This is a bug-like error that is recommended to set the rough constant to 0.1 or 0.5. For the boundary condition of the liners, I consider the convection boundary condition as well as the body, and I give it a constant temperature of 500 degrees. In the following videos, I will teach how to give a spatial and non-uniform boundary condition to these liner and the combustion chamber boundaries. For the inflow, I want to give it velocity boundary condition with mass flow of 1.5 kg per second. In the 3.1 version, the pull from its region does not work and you need to add the species manually. It is the same species you entered for the region. In the outflow, I disable the backflow and also give the same pressure as the coolant boundary. Now we go to the steady state monitor settings. I consider an average temp for the outlet, a max temp for the coolant domain, and a max temp for the engine body domain. Consider the static monitor as 0.05 and the sample size as 0.1 seconds. Give 0.005 for the tolerance and change the file name of the average temp for outlet flow to the area average flow.out. Repeat this process for the max temps and also choose the right streams for each of them. For more accuracy, I changed the turbulence model to K omega SST. The supercycling settings means that the converge solves both solid and fluid domains separately. After each cycle ends, converge averages the results of the walls of each domain and transfer them to each other. This will help the unequal time scales of the fluid and solid domains, and also it can help speed up the calculations. Because I want to do a test simulation, I will set the mesh size to 10 mm. To improve the fluid domain solution, we can use the adaptive mesh refinement. Here I want to consider the velocity scale as 3 and temperature as 2. Make them all permanent. Here I need to refine the whole coolant domain and also improve the walls mesh with fixed embedding. I do this for coolant interface, liner walls, and also coolant region. Here you need to give your own output and post-processing settings. After ticking all the settings, by using the Run Converge option, I let the calculations begin. Because we consider the mesh to be very coarse, the calculations are done very quickly. Now we can use post-processing softwares like TechPlot or ProView to see our results. For that, I open the TechPlot and just drag and drop the output file. Here I use my own macros, which are very effective to see the results faster. In the future, maybe I will teach you how to make these macros. Here we can see the temperature control on the engine body. I want to cut this domain in half using slice and my own macros. By hiding the engine walls, we can also see the results of the water jacket. Now I want to show the streamlines inside the water jacket. For that, change the streamline format to volume road. Select the arrow and drag on the domain. Now we can reduce the size of the ribbons from the road and ribbon section and also show the velocity control on them. By displaying the engine body and increasing its transparency, we can see the entire geometry together. Thank you very much for watching this video. Don't forget to hit the like button and subscribe for future videos. Have a nice day.